authored 3 books. His first one was on the 10 Assumptions of Science, and the second one, The Scientific Worldview. Great books. I think they're all back there. And his latest book was co-authored with Steve Puetz, who's also been active with the NPA and a big help to me in helping to edit the proceedings. And I'm drawing a blank. Glenn, what's the name of the book?
Universal Cycle Theory.
The Universal Cycle Theory, yeah. And Steve also wrote another book about cycles, which I think is also here. So please do look into those books. Anyway, Dr. Glenn Borchardt has been a mainstay in the NPA for a long time, and his ideas on just the philosophy of science are great. He's going to apply them today to gravity. So, Dr. Borchardt.
Thank you. Well, wake up. Let me see if I can figure out which way this works. Well, I probably have given 50 or 100 talks like this. This is the most important one right here. Neomechanical gravitation theory, and again, this is with Steve Puetz, and he's in our Honolulu office. We are Progressive Science Institute. Oh, you can't hear, can you? I'm going to carry this around with me. How's this?
Good.
Is that okay?
Good.
All right, great. Yeah, Steve is in our Honolulu office, and he is a super genius and has really gotten me into this stuff really big time. When I started, I was a Lesage guy. I didn't believe in the idea of gravity being an attractive force or action at a distance, and I was into push theory, and he convinced me elsewise. Now, the outline of my talk, I'm going to really emphasize the assumptions, and I'm going to talk about what we mean by neomechanics, gravitation and the formation of matter, that's a big part of this theory, vortex formation and dynamics, gravitational pressure gradient is what we're talking about here, and gravitation as a local phenomenon. These are the 10 assumptions of science. Back there, this would be called Borchardt Light. It's only $10. Should get a copy sold in the back of the room. Fundamental assumptions. I realized that the Big Bang Theory had to be absurd, and that a lot of the relativity stuff was absurd, and so I got to looking into fundamental assumptions. And the thing about fundamental assumptions, Collingwood from 1940 taught me that they always have opposites. They can never be completely proven. For example, finity and infinity. You can't go to the end of the universe and prove it. You can only assume it, one or the other. Whichever you assume really makes a big difference, as I'll show. If there's more than one assumption, they must be consupponable. What that means is that they can be assumed without contradiction. So I'm going to be assuming infinity, and all my assumptions will include an element of, oops, wrong way. I'm not going to cover all 10 of these, but I'm going to cover the ones that we're going to use in this talk. Inseparability. Just as there is no motion without matter, so there is no matter without motion. I won't be giving the arguments for these. That's all given in the book. Conservation. Matter and the motion of matter neither can be created nor destroyed. Notice I didn't use energy. Normally energy is used, and it is the first law of thermodynamics. We use matter and motion of matter for a reason. Complementarity. All bodies are subject to divergence and convergence from other bodies. What we're getting at here is this is a complement to the second law of thermodynamics, which essentially is a law about divergence. Complementarity is a law about convergence. Again, as I mentioned, the universe is infinite, both in the microcosmic and in the macrocosmic directions. Now, Aristotle believed that the universe was microcosmically infinite. Each particle was subdividable. And I believe Newton, at one time at least, thought about macrocosmic infinity. And this assumption changes classical mechanics to neomechanics. Relativism. This is very important for what we're about to talk about. All things have characteristics that make them similar to all other things, as well as characteristics that make them dissimilar to all other things. When we do math, we typically assume things are identical. like two electrons, for example, are identical. Not so. There are no such things. This is why we don't have two snowflakes, for example, that are identical. I was walking on the sidewalk today and saw a lot of gravel lying about. And I'm going to say, I'll give you $100 if you can bring me two pieces of gravel that are identical. That's my support for the theory, and among other things that we've seen. Interconnection. All things are interconnected. That is, between any two objects exist other objects that transmit matter and motion. Not only is that true, but there is also space as well as matter between any two objects. Infinitum. Univiral determinism is the universal mechanism of evolution. It's our philosophy in the Progressive Science Institute. It says what happens to a portion of the universe depends on the infinite matter in motion within and without. See how that all follows from infinity. In fact, what happens to you is going to be determined by what's inside of you and what's outside of you. Right now, I'm outside of you, so you're going to be influenced by that, even if you're sleeping, perhaps. Classical mechanics, the first, second, and third laws. First one is simply an observation, P equals mv. Second one describes a cause. V has to hit, or object 1 has to be hitting object 2, and the velocities are going to change. Third one says you have equal and opposite effects. This is neomechanics, assuming infinity. Notice that what we like to do is not show a spherical object. This object is irregular. Any irregular object has particles within it. And what we show here is what we call submicrocosms within and supermicrocosms without. We also have then sub-submicrocosms on infinitely so. And here we show an example of the absorption of motion. This is just simply hitting another submicrocosm and transmitting motion from one to the other, and this is explained in the scientific worldview in more detail. Complexification. This is critical to our theory. Gravitation is a local interaction between free, active ether and complex ether. Complex ether is what we know as baryonic matter or ordinary matter. Now, if we had done what the atomists thought to make a universe out of identical atoms, we wouldn't have a universe. And the reason is that particles have to be different for them to actually form a complex. Here we show a larger particle and a smaller one, and other particles around here that are beating it up, essentially. They're impacting it. Large ether complexes experience uniform pressure when they're far apart. These are smaller ether particles, and then these are large ether complexes. Obviously, if they're close together, they're going to be hit by the outside here, but not as much in the inside. And this is the typical equation that we hear from Newton, essentially. This is essentially what he's talking about. Now remember, I was mentioning about infinite submicrocosms. Here's an example. We have, essentially we're going to talk about from now on mostly ether 1 particles, but here we call ether 2 particles being pushed together by ether 3 particles. So these are complexes here of this. Now this is where the universe comes from. If you talk about the universe, it always goes on and on. There's no beginning, no end with this theory. Here's what happens in your swimming pool. Look at these. Beach balls are pushed together because they're getting beat up by their surroundings. Just kind of imagine that this is ether here. There's a whole bunch of them. This is an ether complex. Obviously somebody has been swimming here and they pushed all these beach balls to one end. Here's what we're talking about. Highly active ether particles impact a less active ether complex. So active ether produces less active ether, baryonic matter. Less active, what does that mean? It's not moving as fast. Ether particles probably move near the speed of light. They don't go very far, but they move really fast. In air, nitrogen molecules move at something like 100 miles an hour. Sound only travels at 700. How fast these things move, I don't know. But they obviously do move, and that's what they're doing. They're pushing on this. Now, the second part of our theory is vortex formation. It involves advanced complexification via rotation. What is that all about? Well, look at here. It's more shelter from the macrocosmic storm. These are sardines in what they call a shoal, and they're going around in a circle for a reason. They are going to be protected from the macrocosm, everything outside of them. And this is what would happen for the ones on the edge. And you see this phenomenon all the time, this rotation, which protects the center. You've heard of that one, covered wagons. Protection from the macrocosm. Here's an example of a vortex of a hydrogen atom. Saturn is a vortex. Here is a proto-solar system. Maybe Einstein was right. Here is a little bit of curved space. More curved space. Andromeda. And this is M101 supercluster in Virgo. And so galaxies do the same thing. We did a little experiment as part of our study, and this is really simple. You take sand and pepper and water, and what you do is you rotate it. Guess what happens? All the bigger particles, the heavier ones, go to the center. This is Stokes' law, which describes this kind of gravitation. Essentially says that the velocity of a particle responds to g, which is, of course, a gravitational acceleration. This is Stokes' law is applicable only to the Earth, and that the density of a particle and the density of the medium are really of import. So that the greater the density of the particle, then the faster the velocity, and then the viscosity of the medium, of course, makes a difference. And Galeev in 2002 actually measured the velocity or the viscosity of the ether. If you want to know where that paper is, it's published in the Ukraine, translated English, and I have a reference in a Scientific Worldview book. Now here's an example of vortex, of course, is the Earth. And the big characteristic of a vortex is that the center is more dense than the outside. So here you see the density of the core of the Earth, and then as you come to the crust, it becomes less. The atmosphere shows the same thing. There are two things that you have to remember about vortex. Vortices accrete when they're first rapidly rotating. Here's an example of Jupiter and 4 of its moons. Jupiter is accreting. It is gathering matter. It's rotating very rapidly. Its rotation is on the order of 20 hours. Remember, the Earth rotates in 24. The other end of the stick, excretion. When the rotation slows, like here is Venus, it has a rotation of 2,800 hours. It takes almost a year for it to rotate once. Its velocity is a little greater than the Earth. That doesn't seem to be important. It's the rotation that's important. The excretion is great. The atmosphere here is 90 times as dense as the Earth. It has 95% CO2, carbon dioxide, and about 5% sulfuric acid. So it's excreting. It doesn't have any satellites. There's no moons around Venus. And it's also retrograde, which probably means that it was captured. This is essentially what we're talking about. Here you see ether density, that's the red, increases while the baryonic matter density decreases with distance from the center of the vortex. So they say this could be the Earth, the galaxy, which might have a, what they call a black hole here. Anyway, this is what you're seeing, that the pressure increases as you go away. So wherever there's matter, there's less ether. Where there is no matter, there is more ether. There's another little illustration of it. As you know, the atmospheric pressure gradient looks like this. You have less air molecules in the thermosphere, and then as you get to the troposphere, you have more. So the pressure is greater here. Here is some pushing by unseen baryonic matter, which after all is what we're talking about, unseen matter. We consider ether to be matter. It's just a different form. Here we have, now why is this helium balloon doing this? Well, it's simply because the pressure is greater on this side than this side, obviously. Over this short space, right here, this is enough to push this thing up in the air and counteract the ether push from gravity. Here's what we're seeing. Higher pressure for ether particles, that means right here, there's more room for ether. Active ether, remember everything else is complex ether, slower. This is the active stuff. This stuff is really moving fast. So that's the gravitational pressure gradient that we're talking about, and that's essential to this theory of gravity. Guess what? You can read that. Well, this quote was given to us by Duncan Shaw, who has been reading these old things like, hey, optics. And he came up with this, and this is his theory. This is Newton's theory. How many of you knew that Newton had a pushing gravity theory? Here's one guy. And Carl, you knew? Anybody else? Guess what they hang on him? Action at a distance or attraction? But he had this all along. And this was, we found this, Duncan gave us this quote after we were all done with our work.
He also rejected it.
He rejected it, right. He rejected everything. And he never had hypotheses, right? Well, that's all he had, hypotheses. But yeah, it's the same thing. He's saying the same thing. Now, he obviously had some different ideas about whether this ether was a finite particle and so on. But nevertheless, look at how interesting this is 300 years later. Okay, conclusions are that gravitation is the interaction between free, active ether and complex ether. Neomechanical gravitation is local. Vortex motion concentrates complex ether, resulting in increased complexification. Remember, you're getting, by rotation, you're getting these complexes of ether together, and then you end up producing bigger and bigger complexes, like drag, for example. Ether concentrations are highest where baryonic matter concentrations are lowest, resulting in a gravitational pressure gradient around all bodies. So it's not just only the solar system, but it's all the various parts of the solar system that also have a gravitational pressure gradient. Now remember, we only stepped into this at one place. That is what we call ether 1. The same stuff happens for ether 2, ether 3, and on to ether infinite, whatever that is. So all these particles do the same thing. And they're all in motion, and they all have faster motions until they end up being complexed, and each individual particle is different from all the other particles. That should blow your mind a little bit. But it's the same. You have a choice now between the Big Bang Theory, which is an explosion of the universe out of nothing, or you can have an infinite universe. Pick either one. Are there any, wait a minute, let me push this here. Give a little pitch for our book, Universal Cycle Theory. It goes into details about neomechanics of the hierarchical infinite universe. And the idea is that you have all these vortices, and Here, this little red dot, that's the observed universe. And this is the local megavortex. So we are not pushing here an idea of a multiverses or parallel verses or any such oxymorons. But what we are pushing is a hierarchical universe. There is no end to this hierarchy. It goes all the way up and all the way down, and that's the main point that we have here. I suppose one could have a little bit of expansion or contraction in this. Remember, every microcosm in the universe is either expanding or contracting at any particular moment. So I suppose it would be possible to have some, but you wouldn't have an expansion from nothing. I'm quite sure of that. Okay, are there any questions?
We got 9 minutes.
Okay, I got a quick one. What you call complexified, it seems to me pretty much the same thing as what Don Riddell is calling condensed, or would you know?
Yeah, more or less.
Just come.
Yeah.
Okay, I just wanted to clarify.
Yeah, it's just bringing things together.
Any other questions? Come on up.
I understand the ether you talk about is related to gravity, but my question is your ether also playing the complete role of light medium?
Okay, is the ether a light medium? I believe so.
Okay, then next question. If yes, don't you have to account all the light speed data so far?
What was that again?
If okay, the first question you said yes, your ether is also playing the role of light medium.
Oh yes.
If your answer is yes, then don't you have to explain all the current light speed data using your theory?
Oh yes, right. I can go into that. Thanks for that. Okay, how does this affect light speed and so on? Obviously, we do think that light speed is probably faster in the intergalactic regions because the ether there is denser. Yes, Carl?
Well, I don't know if I should approach.
Go ahead. Just
please do.
Sure, no problem.
If it would save time if you have a question, get in line and then we don't have to wait for you.
Okay, Carl?
The first part about it is just kind of a comment. Thank you for bringing up the point that Newton did conjecture when it comes to gravity, and it isn't true that he had no thoughts on the cause of gravity, but it is my understanding that I don't think Newton voiced or had a lot of thoughts on the cause in his younger age, but in his latter publications of the optics, which is one of his latter works, optics, it's there when we finally find out that he did have thoughts about the cause of gravity, but few people understand that. They only remember the principles and so. And I think that Newton also says, I could be wrong, in some paragraphs below what you quoted, that he compares the effects of gravity being able to attract things to light as it goes from a thin media to a thicker media. It bends toward the thicker stuff. And so he's thinking that I may have it vice versa, and so might Newton. But so I think he compares it at one point to the changes in the direction of light going to and from different medias. I'm a little bothered by one thing on a centrifuge. How would you describe that? As a centrifuge, we know that it would seem that it separates the low-density particles from the high-density particles by throwing the high-density stuff outward. Is that consistent with what you have presented?
Yeah, I would think so. That's part of what a vortex does. Remember, the vortex also throws ether particles out
I see.
because they're tiny. Remember, they're very tiny. Remember the R that I had in the Stokes equation there? The ether particles, there might be a billion of them in an electron, as far as I know. So they're really tiny. They tend to be thrown out as well.
Thank you.
Yes.
Hi, my name is David.
Yes, David.
Two quick question is, does the direction of rotation matter in the vortex?
Well, does it matter for what? For what we're talking about here, no.
No. Okay.
No.
So if you have counter-rotating vortexes, one's going counterclockwise and the other one going clockwise.
Right. That's very perceptive. In fact, one of the things I brought up a couple of years ago was that electron probably is an ether vortex, like a little dust storm, that's rotating maybe counterclockwise, right? And then a positron would be rotating the other way.
Yep.
And then when they annihilate is when they crash together.
Yep.
So we're on the same page. I'd like to talk to you.
Another thing too is, I guess you're saying that like attracts like. So if there's two of you out there in universes, you attract so fast so that you become one again.
Don't think that would be. At one time I thought there's another Glenn Borchardt probably in another universe or part of the universe.
Oh, no.
And no, because of relativism, and I mean relativism, there's similarities. There's probably some guys similar, but not the same.
If there's sameness, it'll come together with perfect.
Yeah, well, don't know about that.
Pound again.
A difference is a track too, you know. That's why I have a wife that's female.
Okay, great. Thanks, everybody.